Well, I did it again. I forgot to hit record when we did our lecture this morning, and I hate it when I do that because then I got to go through the whole lecture again. So this will be a repeat of this morning's lecture so that you guys have a video that you can use to study. So here we go. Let's get into it. And we're going to be talking today about the empirical formulas and molecular formulas that come from elemental analysis. So this is kind of an involved problem, and so we have some intermediate problems and some introductory problems. The first one too is how to use Avogadro's number in terms of converting from moles to atoms or atoms to moles. And so let's do a quick problem related to that one. So this first problem that we did this morning was out of Alex. An iron atom has a really small mass, as you can see here, and then it has another random fact that they weighed this cooking pot and it had a mass of 0.5 kilogram. So the first question is, what is the mass of 1 mole of iron atoms? So we have this mass of a single atom, and we need to know the mass of a mole of those atoms. And one of the principles I teach in terms of chemistry knowledge is in any kind of problem solving is to start with the end in mind. And so what's the thing we're going for? We're going for mass of iron. And what we have is a particular mole. We have a mole of iron atoms. That's what's given in the problem. You can see that right here. So right here we're dealing with a mole of iron atoms. Okay, I'm messing with my video here. Okay. So we got 1 mole of iron atoms, and we want to know what the mass is. So we're going from here to here. So this is where we're starting, this is where we're ending. So you've got to know where you're going, okay, and where you're starting in any of these problems. So if you have that mindset of if you got to know where you're starting and you got to know where you're going in doing problems. So we got 1 mole of iron atoms, and Avogadro's number is what tells us how many particles are in a mole. So this allows us to cancel this unit of mole and get into atoms of iron, okay? And we know that 1 atom, from our problem, 1 atom of iron weighs 10 to the minus 23 grams. Okay, so we've got the atoms here, they cancel. And so we've got a little tiny mass here, but we got a whole lot of atoms, and so it comes out to be a number that's reasonably large, something we could weigh out in the lab, 55.8 grams of iron. So that's our answer. Now this was, if you were to look at the periodic table, this also matches the periodic table, 55.8 grams per 1 mole of iron atom. So that's the entry on the periodic table. Okay, now let's do the second question on this one. How many moles of iron atoms have a mass equal to the mass of this cooking pot? So again, where are we going? We're going to moles of iron, right? So that's what the question was asking. How many moles of iron have a mass equal to the mass of the cooking pot? So we're starting here with mass and we're going to moles. So we start with 0.5 kilogram. We want to get out a kilogram because we've got this is the mass of 1 mole and it's in grams. So we're going to get out of kilograms. So your unit analysis, we get rid of this kilogram and we're in grams. And then we use that molar mass. We can say you use it upside down, right? So we've got grams on bottom so that they cancel with this gram and we end up with a mole of iron on top. So that's where we wanted to be. We're moles of iron. So 8.96 moles of iron is our answer. So this is the way we use the molar mass. We can use it right side up with the 55 grams on top and moles on bottom, or we can use it upside down to get out of grams and into moles. Some of these problems require a knowledge that some elements come as diatomic species. And so if you look at the periodic table that I give you on the exam, you'll notice that some of the elements are bold, some are italics, and then some are just regular. And so the italics ones, like bromine here and mercury, those are liquid, have room temperature in 1 atmosphere. The bold ones here, like radon, are gas. So all of the bold ones are gas. Now, when they form a gas, do they stay as a single atom? Yes, for the noble gases, these are what we call monatomic gases. okay? But these yellow molecule or yellow atoms here form diatomic gases. So you see there's two of them in each. So nitrogen in nature at 1 atmosphere and room temperature is a gas, and there's two atoms of nitrogen in that molecule. 2 atoms of oxygen, 2 atoms of fluorine, 2 atoms of chlorine. So those are diatomic. And hydrogen does the same thing, so H2. So all of these yellow ones are diatomic gases. So if you're looking at a problem and it says like a hydrogen and oxygen get together to form water, you know that hydrogen is H2 and oxygen is O2. So it's not H plus O, it's H2 plus O2 form water. And so when we balance that reaction, we know we need 2 waters because we need 2 oxygens, and that means we need 2 hydrogens. So we have 4 hydrogens on either side and 2 oxygens. So there you go. This is a situation where you need to know that when I say hydrogen gas, it means H2. When I say oxygen gas, it means O2. Okay, so here's the example of that. We got a nitrogen gas that participates in this reaction. And the chemist measures 0.45 moles of nitrogen gas. What's the mass of 0.045 moles? Okay. So this is an example. We're going to mass, and we start with moles. So how do we get out of moles and into mass? We need the molar mass, and this just says nitrogen gas. So we need to know that nitrogen gas means N2. So regular nitrogen atom, we go to the periodic table, we see it's 14 grams per mole, but if it's N2, then it's 28 grams per mole. So we've got to use that molar mass for N2 in our problem here. So the moles of nitrogen cancel here. And now we're into mass of nitrogen, and that happens to be where we want to go. So 0.045 times 28 gives us 1.3. Now, one of the terms that I introduced today is a term that I coined as the way I teach chemistry. And these chemical reactions happen in terms of atom to atom or moles of atoms. But in the lab, we measure things out with mass and volume. So I call these units chemistry units or chemical units. And I call things like mass lab units. Because in the lab, we have scales and balances, and we have volumetric glassware and so on. So we measure things in lab units, and we convert them to chemical units to do the chemistry, and then we convert them back to lab units. So this particular calculation is one where we're converting away from chemical units and into lab units. So this phrase, chemical unit and lab units, that's my, you're not going to find that in a textbook. So that's why I'm emphasizing that this is the term that I use. But it's a good mental concept because we're going to be using lab units of different types, things, partial pressures, volumes and concentrations, and masses. So converting those to chemical units is a very important skill. So if you have trouble with dimensional analysis and unit conversions like this, then this is going to be a really hard course. So you need to be really good at this type of calculation because this is a small piece to a larger puzzle. You also need to be very good at calculating molar masses. So here's a formula HF. It's talking about measuring 0.08 moles of this. How much mass is there? So we're going to grams of HF. We're starting with moles of HF. So we need to know the molar mass. So I always do these in the table format. I got 1 hydrogen, so that's a mass of 1.01. 1 fluorine, which is a mass of 19. Add those together, you get a molar mass of 20. So now we can go to our problem. We're starting with 0.08 moles of HF. These are chemical units. We're going to convert them to lab units. So multiplying that by 20 grams per mole for HF, we end up with 1.6 grams of HF. In order to calculate those molar masses, sometimes you need to calculate, more complicated molecules like this one. Sometimes you don't have to go to to mass, sometimes you can just convert from moles of one thing to moles of another, and you can use the molecular formula for that. So here's an example. So we're wanting to go to moles of oxygen from moles of nickel. So now it's just chemical units, so we can use the chemical formula to do this conversion. So if we say that 1 mole of nickel, that's equal to 4 moles of oxygen because of this 4 right here. So we can use that as a conversion factor. So we can see that in this molecular formula, from nickel, there's 1 mole of nickel and 1 mole of this formula, but then this formula has 4 moles of oxygen. And so again, if we were to cancel everything out, we would be canceling the nickel, we'd be canceling this formula here, and we would multiply 4 by 0.022, and we'd have that many moles of oxygen. So 0.088 moles of oxygen. And notice whenever we're using chemical units, and chem units, so when we're staying within the chem unit thing, we can use the chemical formula to do that conversion. We don't need the molar mass because we're not doing anything with molar mass. So this actually this title doesn't really go with this problem. So that must just be a copy paste error. So, okay, so now we're doing another one where chem units to chem units. So we'll just scratch this piece out. But it is an example too of this type of problem in ALEX. So here we're going from moles of oxygen to moles of hydrogen. So we're starting with moles of oxygen. We want to go to moles of hydrogen. We're staying within the chemical units area, so we can just use this molecular or chemical formula here to do the conversion. So I simplified things, and I just put the hydrogen on top and the oxygen on bottom. Now, where did these 12 moles of oxygen come from? It's 2 times 5, right? 2 times 5 here, plus another 2. So 2 times 5 is 10, plus 2, that's equal to 12. So there's the 12 oxygens. And then I have this parentheses here for the hydrogen, and so there's 2 hydrogens. So we can just use this chemical formula to convert chemical units. And so we're going from oxygen to hydrogen. So the oxygens cancel, and we have hydrogens left over. So we have 88.8 times 2 divided by 12. So we end up with 14.8 moles of hydrogen. This one's a little more difficult formula just because there's more atoms in terms of finding the molar mass. And so I always do these in a table. It's slower, but it's always right. If you're trying to do this in your calculator with parentheses and everything, it's a source of error. So unless you're super confident in that, you're probably going to screw it up. So to do this, in your calculator, you would type in 40.1 plus 2 times 16 plus 2 times 1.01 equals, and you would end up with 74 grams per mole. Sounds pretty easy, but people end up screwing that up sometimes. So doing it in a table, you can sort of extend this. 2 times 16 is 32. That's easy to do. 2 times 1 is 2, so that's easy. And now we can add up 40 plus 32 plus 2 to get the 74. So this is slower, but guaranteed to work. And it's obvious you got all of the atoms that you need in the formula calculated. Okay, now we really start getting into this experiment from elemental analysis. And so an elemental analysis experiment, we do this a lot of times with combustion. So we'll take an unknown substance and we'll burn it in oxygen. Before we do that, we set up the exhaust gases and we run them through these little cartridges that we weigh. So they're like absorbent cartridges. And they have cartridges that will absorb only CO2 and other cartridges that will only absorb water and others that may absorb sulfur or nitrogen and so on. So we weigh out all those cartridges. We hook them up to the exhaust. We burn the fuel with excess oxygen. the CO2 goes in and gets stuck on the CO2 cartridge. And the water goes through the CO2 cartridge and gets stuck in the hydrogen cartridge. Finish the experiment, we weigh the CO2 cartridge and we see how much more mass it has. We divide out the mass of the oxygen and we have just the mass of the carbon. And then the same for the hydrogen, the same for the oxygen. And so we end up with a percent mass of all of the elements. So that's elemental analysis. And so once we have that elemental analysis, we can get the empirical formula. So let's go through these different parts to this process. So a certain compound has the percent composition from this experiment of 40% carbon, 6.7% hydrogen, and 53% oxygen. So mentally, it's good to just pretend you have 100 grams of this substance. So if I have 100 grams, what does percent mean? It means per 100. So that means I've had 40 grams of carbon per 100 grams of substance, or 6.7 grams of hydrogen in 100 grams, or 53.3 grams of oxygen in 100 grams. So this is nice. I can just take those percentages and I can make them grams. And then I divide each of those partial masses by the molar mass of each element. So if I have 40 grams of carbon, I can divide by 12.01 grams of carbon per mole, and I get the moles of carbon. So 3 moles of carbon, 3 1/3. I can divide the hydrogen by hydrogen's molar mass and see that I have 6.6 moles of hydrogen. And if I divide the 53 grams of oxygen by 16, then I get the 3 1/3 moles of oxygen. So this is the empirical formula. It's just not whole numbers. We'd like to get whole numbers. And so I can divide all of these by 3.33 and see if I get whole numbers. So that's the next step. Divide all of those element numbers of moles by the smallest value to get a set of integers. So the smallest value of those was 3.33. So if I divide the carbon number of moles by 3.33, I get 1. So 1 carbon. If I divide the hydrogen by 3.33, I get 2 hydrogens. And if I divide the oxygen, I get 1 oxygen. So now we have nice, beautiful whole numbers, and that's the empirical formula from this elemental analysis. So that's how we come up with the empirical formulas. The word empirical means experimental, and so this is an ancient type of experiment. So this is how we came up with the percent composition of substances and their empirical formulas. Let's do another one. So measurements show that this compound X has this composition of 42.8% carbon and 57.1% oxygen. If we pretend that we have 100 grams of this substance, then that's 42.8 grams and 57.1 grams. Let's divide that 42.8 grams of carbon by 12.01, so we get 3.6 moles of carbon. We divide 57 by 16 and we get 3.6. They're the same amount of each. So this empirical formula, if we divide by 3.6, we end up with 1 carbon and 1 oxygen. And so our empirical formula would be CO, carbon monoxide. We don't write the ones if it's 1. If it was a 2 or a 3, we'd write a 2 or a 3, but we don't write 1. So that's a simple one, all on one page. Do this in your notebook, type the answer into italics. Now, that's the empirical formula. That's the simplest set of whole numbers in terms of the subscripts, okay? The molecular formula may be something totally different. Like this may not be carbon monoxide. This may have the empirical formula of CO, but it might be like, I don't know what element, what molecule it would be, but it might be C2O2, kind of like hydrogen peroxide on the test. The empirical formula was OH or HO, but the molecule, hydrogen peroxide, is H2O2. So this molecule might be C2O2 or C3O3. How would we know that? Well, we need to do a different experiment to know how the molecule behaves. A lot of times we can do that with gas experiments because the pressure, temperature, and volume of a gas depends upon the number of particles. So if it was C2O2, then it would behave. I could put a known mass of this substance into a balloon and I could measure its change in volume with temperature, I could see that it behaves as a certain number of moles would behave. And so I know how much mass I put in there. Now I've measured the number of moles and I've got a molar mass. So the molar mass is needed to turn an empirical formula into a molecular formula. And this is how you do it. So here's an example problem. A certain compound has the empirical formula CH2O. If we did some other experiment and we realized that 1 mole of that substance weighs 120 grams, then we know the molar mass of the substance. And so we would use that molar mass to determine how many of these empirical formula units we have to make the molecule. So this is the molar mass of the whole molecule, and this CH2O is only the empirical formula. So it's got CH2O times some number of units of that to give us 120 grams per mole. So what is the mass of this piece right here? Well, that's 12 plus 2 plus 16. So that's equal to 30 grams per mole. So some multiple of 30 grams per mole will give us 120. So we can divide 120 by 30, and we can see that N equals 4. Because 30 will go into 124 times. So now we know the molecular formula is C4H8O2, because that's CH2O times 4. So I have 4 carbons, 8 hydrogens, and 4 oxygens. But without that molar mass, we can't know what the molecular formula is. We could only know the empirical formula. Okay, let's do another one. So now this molecule has 60 grams per mole. So it's a totally different molecule, but it may have the same empirical formula. So if we look at this, 46.8 and 53, it looks very similar to the one we did before. Not exactly the same in terms of its percent composition, because every experiment is a little different. But we divide the 40 for carbon by 12, divide the hydrogen by 1, divide the oxygen by 16, and we end up with 3.34 moles of carbon, 6.7 moles of hydrogen, and 3.32 moles of oxygen. What's the smallest value of this? 3.32. So we divide all 3 of those by 3.32, and we get something close to integers. All right, 1.01 carbons, hydrogens, and oxygens. These are close enough to 1, 2, and 1 for us to say the empirical formula is CH2O. Okay, so these 3 numbers right here go right here. 1, 2, and 1. Now, that piece weighs 30 grams per mole. So our molecule is some number of units of that to get to 60 grams per mole. So we have some number, integer number, times 30 to get to 60. So 60 divided by 30 is 2. So our molecular formula for this substance would be C2H4O2. Now sometimes we end up with some funny numbers here. Like we might end up with, let's say, 1.5 carbons. And so if we ended up with that situation, we would multiply everything by 2 to get rid of that 1.5. Because this would be a C1.5 H2O. And I don't like that 0.5, okay? So we're going to multiply everything by 2 to get rid of it. So 2 times 1.5 is 3. So this would be C3H4O2. So that's what you do if you have a 1.5. What if it was a 1.67? Okay, what is that one? That one is 1 2/3. Okay, so 0.67 is a 2/3, or maybe it's 1.33, which would be 1/3. Well, I'm going to get rid of that third by multiplying by everything by 3. So if this was C1.67 H2O, I'm going to multiply everything by 3. And so that's going to be 3 plus 2 more. So that's going to be 5. C5, H6, O3. Because I multiplied everything by 3. And so that's what you would do if you had like a 0.67. If you had a 1.33, then that would be like this C 1.33 H2O. And so that's again not good because it's not a whole number. And so I'd multiply this one by 3. Okay. And so it'd end up being C4 H6O3. So that's what you do if you end up with these odd ones. After you divide by the smallest number of moles on all 3, it doesn't always work out to a whole number. So you're looking for these things like 0.33, 0.67, or 0.5. And I think those are going to be the most common ones. So we'll just leave it at that. Okay, so I think we're good. That's again the hardest set of problems in this module. So you'll be set for tonight, and I think that's pretty much everything I said in class. So you didn't miss anything, and we'll talk to you later.